Welcome to AP Podcast 14.6. This is on bases. And unlike acids, when people hear acids, ooh, that sounds scary. They think it's going to be very corrosive, which it is, of course. Bases are just as corrosive. But you don't usually hear people going, oh my gosh, it's a base, because they just don't know it that much. But if you look at bases, what we're used to is seeing those things with an OH, right? Any kind of hydroxide is a base. And as you already know, the alkali metal hydroxides are already strong, and that is because they completely dissociate in water. Also the component of being a strong base. Something that we kind of focus on but maybe aren't totally aware of all the time is the fact that if you have an alkali earth metal and you have two hydroxides, that's a dibasic basic. Now di meaning two. And you guys know that when this breaks up into water, you get two OHs. However, they don't dissolve that well in water. But if I'm reacting this thing with an acid, something like HCl, we get two OHs for every one calcium hydroxide. And we have focused a lot on that this year. Hopefully that's something that's kind of ingrained in your brain by now. And then just as an everyday aside, we use these alkaline earth metals, mostly calcium hydroxide, as antacids because the OH will not dissolve in a stomach acid unless it's being attacked by the acid. So the hydroxide doesn't build up, it only gets used up as the acid attacks it. So the Tums for your tummy is usually calcium hydroxide. Now, there are other bases out there, and there are bases that if we think of the definition of a base being a proton acceptor, there are quite a few out there, all right? And ammonia is probably the one that's most commonly referred to, the one that your book will refer to the most, and I'll refer to also. And the way it works is if you think about an ammonia molecule, we've got this lone pair right there. Remember this from way back when? We've got that lone pair. And imagine we've got a water here floating around. Now it turns out that this H can break off the water and is attracted to that lone pair. And so then what you're left with is, of course, an OH minus. So notice what a base without OH does. What it does is when it combines with water, it forms a hydronium ion, but it also, more importantly, forms a hydroxide ion. So that's kind of the way it works. It turns out that we see that most often with molecules that have nitrogen in them because they so easily accept that proton. And it's just something that you will see with many weak bases, that they do contain that nitrogen ion. So if I'm going to write out the equilibrium expression for this, again, we won't put water in there, right, because it's in the liquid state. I get the base, whatever it happens to be, over the base plus the hydrogen plus the OH. And then look at this, another K. But this isn't Ka, this is Kb. B for being base. So we've gotten K, KEQ, KC, KP, KA, KW, and now KP. That's a lot of Ks. So anyways, we'll be doing some problems like this. And the nice thing is they're done just like acids, except that, of course, we're dealing with some bases. So here's just some basic points about the strength of bases. And let's calculate a couple problems just to make sure we're on the right track. Calculate the pH of a 0.05 molar NaOH solution. Well, again, the challenging part to this problem is just realizing that this is a strong base, and that means I have 0.05 molar of OH minus, right? So again, take the negative log of that, and you get a pH of... Oh, wait, pardon me. I can't believe I just said that. There's one slight problem. If we take the negative log of that, we get a pOH of 1.3, which would then, sorry, I'm running out of room, give me a pH of 12.7, which is what we'd expect because we know this is a base, and that is a very high pH, and high pHs are what bases are, right? Calculate the pH, the OH, and the pOH of that concentration molar calcium hydroxide. Go ahead and do that problem right now, and I'll write the answers and see if you get it. All right, so is that what you got? Now, of course, on this problem, the main challenge is dealing with the fact that you've got two hydroxides right there, right? So to get that concentration, I just doubled this. And so that was the only sticking point. Now, as far as all the other hydroxides, we consider them weak. They're going to have a small Kb, which makes them a weak base. And so now if we look at these two, which are the stronger base? Well, you know that this right here, which is the anion of a strong acid, that has virtually no affinity whatsoever for ammonia. Pardon me, for ammonia. I'm looking over here. For H+. So this is the stronger base. This one's a stronger base. And then now for these two, really the only way we can do that is look up the Kb. Alright, and this one you've seen numerous times, like 1.8 times 10 to the minus fifth. And this thing, which happens to be pyridine, has a Kb of 1.7 times 10 to the minus ninth. So anyways, the stronger base is of course the one with the bigger Kb. So there you have it. Let's move on to another problem that we can do. So they want us to calculate the pH of a 15 molar ammonia. So let's try this, right? So we solve our problem just like always. Instead of a Ka though, we want to do a Kb. And we get 1.8 times 10 to the minus fifth. And that is going to, again, make x squared on the top and 15.0 minus x on the bottom. And again, what are we going to do with this x right here? We're going to make this problem easy for ourselves, and so we're going to ignore it. And then when you solve for that problem, you get 1.6 times 10 to the minus second. Alright? Now, the thing that's super important here, and this is the mistake that a lot of students will make, because you've got to remember what this x squared is on the top. Remember, for this one it would be NH4 plus and OH minus. Alright? And so what a lot of students will do right here is they'll take that number and they'll take the negative log of that. And they'll write that down as the pH. Notice it's asking for the pH up here. However, they're not asking us for the pOH, and that's really what we'd be calculating here. So you've got to remember that if I ever use a Kb, that's going to give me the OH concentration and not the H plus concentration. So there's two ways to do it. I prefer to just take the negative log of this and subtract that from 14. You can of course divide that into the Kw and then take the negative log of that. So when you work that out, either way you do that problem, you get a value of 12.2. Alright? And there you have it. Alright, last but not least, calculate the OH concentration. I'll tell you what, go ahead and pause the video. I'm just going to write the answers for this, and we'll see what you get. Alright, so there you go. Those are the three answers to this problem. And again, like always, if it doesn't make sense, we'll go over it in class, and we will see you next time.